Imagine a world where a quick, non-invasive scan tells a surgeon the exact boundary of a tumor in real time, right there in the operating room. Or, where a virtual replica of your own heart can predict your 5-year survival odds with uncanny accuracy, maybe far better than any human expert. Sounds like something out of a futuristic movie, doesn't it? Well, today we're taking a deep dive into precisely that, the architectural transformation of modern medicine through artificial intelligence. And this isn't just about small tech upgrades. It's a fundamental reshaping of healthcare itself. Everything from how we diagnose and treat to how entire hospitals operate. Our mission in this deep dive is to really pull out the most important nuggets of knowledge from a stack of truly fascinating sources. We want to help you understand the immense potential AI holds in healthcare, but also the complex ethical tightrope we're walking as we integrate it. And crucially, the strategies being developed to govern this incredibly powerful technology. You'll walk away, hopefully, not just informed, but ready to think critically about the future of your own health and the health system around you. So let's unpack this. Our sources really emphasize that AI's integration into medicine isn't just an update. It's creating these incredibly complex, adaptive systems, places where technology and human expertise are deeply interwoven. Think of it maybe as the algorithmic healer working hand in hand with human doctors and nurses.
Exactly. And what's truly fascinating here is how AI unlocks capabilities that were, frankly, science fiction until very recently. It's moving far beyond simple automation. It's fundamentally changing diagnostics, therapeutics, and even the operational flow of an entire healthcare system.
Hmm.
It's a profound architectural shift in how medicine is actually practiced.
Right.
Wow.
Okay, let's start with diagnostics then. What if we could see changes in your body that are completely invisible to the naked eye? Or reconstruct a full medical image from just a tiny fraction of the usual data. This is where AI's capacity for enhanced diagnostics and precision medicine really shines, right? Fundamentally reshaping how we approach early detection and accurate diagnosis.
Oh, absolutely. This is a monumental shift. AI's ability to analyze vast, complex data sets, and we're talking everything, scans, genetic information, lab results, with, well, superhuman speed and precision. It's transforming medical diagnostics. We're moving from a static, human-centric interpretation of data to a more dynamic, AI-driven analysis, prediction, and even the generation of medical data. That's key. This ushers in a new frontier of precision and early detection that was pretty much unimaginable just a few years ago.
Okay, so one of the most groundbreaking examples our sources highlight is something called hyperspectral imaging, or HSI. Now, this isn't your standard camera. Your phone camera takes a picture in red, green, and blue light, right? HSI, on the other hand, captures data across hundreds of extremely narrow, contiguous spectral bands of the electromagnetic spectrum.
Exactly. So instead of just those three colors, HSI creates what's called a three-dimensional hypercube of data. Think of it like this. Imagine a normal photograph is a flat sheet, maybe, but an HSI image is a cube where every single pixel has this detailed spectral signature. And that signature tells you its unique biochemical composition.
Okay.
And this signature is incredibly important because it allows AI algorithms, things like convolutional neural networks or CNNs, which are essentially very, very good pattern recognizers, to detect subtle changes in cells and tissues, changes completely invisible to the human eye.
So it's almost like a non-invasive digital biopsy.
That's a great way to put it, a non-invasive digital biopsy.
Yeah. The profound implications for surgical oncology, for cancer surgery, are truly remarkable, especially when it comes to getting real-time feedback during an operation. For instance, studies on breast tissue done right there in the lab showed HSI had over 91% accuracy in telling different tissue types apart. And that includes identifying invasive carcinoma with 93% accuracy.
And here's the kicker. That performance is comparable to the current gold standard, which is frozen section analysis done during surgery. But HSI does it significantly faster. It can scan an entire removed tissue surface in minutes, giving surgeons near real-time feedback during that initial operation.
Wow.
Imagine the impact on preventing cancer recurrence by ensuring complete tumor removal the very first time. No more waiting days for lab results, or worse, having to do a second surgery.
Yeah, that's huge. And it's not just breast cancer, right? For difficult head and neck cancers, like oral squamous cell carcinoma, where assessing the tumor margins is incredibly tricky. A specific type of AI model trained on HSI data achieved strong accuracy in tumor recognition. It enabled rapid, automated delineation of those critical tumor margins during really complex surgeries.
Yeah. Right. And even in neurosurgery, HSI is being developed to visualize brain tumor locations, like glioblastoma, which is notoriously difficult to remove completely. A hybrid AI model has already achieved 80% accuracy in classifying tumor healthy tissue, and even blood vessels right inside living specimens in vivo. This provides a crucial real-time map to guide incredibly delicate brain surgeries, minimizing damage to healthy tissue.
That's amazing. And beyond cancer, HSI shows immense promise too.
Definitely. For neurological conditions like Alzheimer's, HSI can non-invasively detect early-stage biomarkers in the retina. This could potentially enable large-scale population screening years before cognitive symptoms even appear. Imagine catching it that early.
Wow.
And for wound care, HSI assesses healing trajectories by mapping tissue oxygenation and classifying tissue types. There's a system called Deep View by company Spectral AI, which uses this technology to predict a complex wound's healing potential on day one, analyzing tissue characteristics invisible to our eyes. This is a game changer for personalized wound management, making sure patients get the right care right from the start.
That's incredible, going beyond what our eyes can see and doing it in minutes. But, okay, it gets even more mind-bending when we look at how AI isn't just analyzing, but actually creating medical data. That's wild.
It really is. This is the realm of generative AI in medical imaging. Think of those generative AI models, the ones behind popular image creation tools. Now apply them to medicine. They're revolutionizing the field by creating and enhancing imaging data, not just interpreting it. And this directly addresses huge challenges like radiation exposure and long scan times.
Right. So for low-dose CP scans, for example,
Yep.
you're saying new models can reconstruct a full 3D CT image from just a minimal number of X-ray views. That drastically reduces the patient's radiation dose.
Exactly. And for MRIs, there was an initiative called Fast MRI, which showed that AI can reconstruct diagnostically equivalent knee MRIs from just 25% of the standard data. That makes scans 4 times faster.
4 times faster.
Yeah, that's a huge win for patient comfort and clinic efficiency. Another fascinating application involves transforming images from low-field, portable MRI scanners into high-quality synthetic scans that look like they came from top-tier machines. This dramatically enhances diagnostic accessibility in resource-limited settings, bringing advanced imaging to places where it might otherwise be impossible.
And one of the most powerful applications of generative AI you mentioned is its ability to create high-quality, anonymized, synthetic medical images. So these aren't real patient images, but they look and act like them.
Precisely. This is crucial because it addresses data scarcity, it helps balance out underrepresented cases in the training data, and it protects patient privacy, all major hurdles in developing robust, fair AI models.
And the quantifiable impact is already being seen.
Oh yes, one study found that AI-generated reports for chest x-rays reduced the average reading time for radiologists by over 40%, from about 34 seconds down to just under 20 seconds. And importantly, it did that while simultaneously increasing diagnostic accuracy for certain conditions. So it's a significant efficiency gain paired with improved diagnostic quality.
That's the double win.
Right. If we connect this to the bigger picture, this move from AI simply interpreting data to actually generating it, it's a profound shift. An AI that can reconstruct a high-resolution CT from a low-dose one isn't just helping. It's creating a new, vital piece of reality for the clinician. This significantly elevates AI's power and utility, but, and this is a big but, it also fundamentally raises the stakes for safety and trust.
How so?
Well, an error in an interpretive model can often be double-checked against the original data, right?
Yeah.
But a hallucination from a generative model creates this plausible but entirely false reality that is far more insidious and difficult to detect. And a flawed prediction, derived from maybe flawed generated data, can tragically set a patient on a completely erroneous and harmful treatment path. This inherent escalation of risk means we absolutely need robust, ethical architectures and governance frameworks baked in from the very start. It can't be an afterthought.
Got it. Okay, building on that predictive power, AI is also enabling a shift from static diagnoses to what our sources call dynamic predictive phenotyping. Can you unpack that a bit?
Yeah, sure. It basically means synthesizing all sorts of patient data, not just scans, but labs, genetics, lifestyle data, maybe to actually forecast future health outcomes, not just diagnose a current state. A really landmark application here involved AI software creating virtual 3D hearts from patient MRI scans. By analyzing the incredibly subtle motion of over 30,000 points in the heart muscle, with each beat something a human eye could never track, the AI learned to predict 5-year survival odds in patients with pulmonary hypertension. And it did it more accurately and far more rapidly than human experts using traditional methods. This isn't just diagnosing, it's truly prognosticating a future state.
That's incredible. And in the world of dermatology, computational methods combining with AI.
Yes, exactly. Imagine using advanced mathematics like fractal analysis to quantify the incredibly complex geometry and texture of skin lesions features that often correlate with malignancy but are hard for humans to assess consistently. This data is then fed into AI models like support vector machines that can differentiate cancers from benign tumors. Commercial AI dermatologist tools, apps you can use on your phone even, already claim over 97% accuracy for over 58 skin conditions, including melanoma, simply from user-submitted photos. And for early detection across the board, AI excels at identifying subtle patterns that act as novel biomarkers. For example, combining AI with thermal imaging can diagnose peripheral arterial disease by detecting minute local body temperature variations, which reflect underlying blood flow abnormalities. AI is also indispensable for discovering complex molecular biomarkers, like finding circulating tumor DNA from a simple blood test, or identifying unique protein signatures from vast genomic and metabolomic datasets. This paves the way for earlier and more precise diagnosis of devastating diseases like cancer, cardiovascular issues, and neurodegenerative conditions, catching them much, much sooner.
So, what does this all mean for your personal health experience for the listener? It points directly to hyper personalization at a scale we've just never seen before.
Precisely. AI's ability to process your individual data in real time allows for the delivery of hyper-personalized healthcare experiences at an unimaginable scale. This goes beyond simple customization. It creates adaptive systems that respond dynamically to your unique biological and behavioral patterns.
And for medical professionals.
While AI-powered platforms can create personalized learning paths for them, dynamically adjusting the content, pace, and difficulty of training modules based on real-time assessments of their comprehension and skill gaps. It's adaptive learning in action, helping ensure healthcare providers are always at their best.
And in consumer wellness, AI is driving a quiet revolution, isn't it?
It really is. Platforms like Noom use AI for personalized health coaching. Apps like Wobot provide AI-driven mental health support based on cognitive behavioral therapy principles, available 24/7. In nutrigenomics, platforms analyze an individual's DNA to provide incredibly hyper-personalized dietary recommendations, truly tailored nutrition based on your unique genetic makeup.
Looking ahead, the future seems to point toward even more sophisticated AI orchestrators, like what Microsoft is developing with its AI diagnostic orchestrator. You're saying these systems could sequentially investigate and solve complex diagnostic challenges that might stump human experts.
That's the vision. These systems could coordinate different AI tools and data sources to tackle really difficult cases. And this concept extends even to creating personalized, augmented, or virtual reality environments, dynamically shaped by AI to support your well-being, learning, or specific therapeutic goals. Imagine VR tailored perfectly to your mental state.
Right. Okay. So beyond diagnosis, AI is moving into these deeply human domains like therapy and even the very environment of a hospital room. Imagine an AI not just as a tool, but as a relational partner or the intelligent core of an adaptive hospital.
This is the rise of therapeutic and ambient AI, and yeah, it's full of exciting possibilities, but also significant complexities. When we talk about therapeutic AI, especially those powered by large language models, we immediately encounter the empathy challenge. Now, research actually shows these AIs can exhibit cognitive empathy, they can recognize emotions, and provide supportive responses. In some studies, believe it or not, AI-generated empathetic responses were even preferred over those of human physicians.
Preferred. Wow. But there's a catch.
There's a big catch. Our sources caution that this capability is often a very sophisticated mimicry of compassionate language, not a genuine contextual understanding of human emotion. Current models can fall into repetitive phrasing, they can be overly sensitive to subtle prompts, or produce responses that are just way too lengthy in sound. Well, robotic, despite the empathy. This creates what's called an empathy illusion. And the risk here is twofold: fostering unhealthy attachment from the user, or, more dangerously, failing to recognize and respond appropriately to high-risk situations like a severe mental health crisis, because the AI doesn't truly understand the context or the stakes. The ultimate goal needs to be true contextual empathy, a deeper, maybe multimodal understanding that goes beyond just clever word patterns.
Okay. But one of the most fascinating and potentially powerful applications our sources explore is AI serving as a cognitive mirror for human therapists. What does that mean?
Imagine an AI analyzing anonymized transcripts of therapist-patient interactions to identify potential blind spots in the human practitioner's approach, things they might not even be aware of themselves.
Like what What could it
Yeah.
spot?
All sorts of things. Latent biases the therapist might hold, logical fallacies in their reasoning during a session, maybe patterns of emotional avoidance, or even subtle empathy gaps. You could engineer prompts, apparently, to create an AI that performs a kind of forensic analysis of conversational patterns. It could deliver unflinching feedback to reveal unconscious defense mechanisms or self-sabotaging narratives the therapist might be subtly reinforcing.
That sounds intense, but potentially revolutionary for training and supervision.
Exactly. This AI-driven feedback loop could be a revolutionary tool for professional development and supervision, potentially helping to reduce therapeutic drift, where therapists stray from effective models and maybe even combat empathy fatigue.
But this raises an important, almost philosophical question you mentioned. If an AI can analyze a human therapist, what happens when it turns that analytical gaze on itself?
Right. And how do we ensure that this cognitive mirror system is built with extreme care so the AI doesn't simply project and amplify its own inherent biases onto the therapist's practice? That's a critical safeguard needed.
This brings us to the emerging field of computational psychotherapy and this more speculative yet profound concept of self-therapeutic AI.
Computational psychotherapy basically uses advanced computational models, particularly those large language models, to simulate psychotherapeutic sessions. The goal here is to test and refine therapeutic interventions in a controlled virtual environment in silico, as they say. It offers a novel way to advance therapist training and maybe even discover entirely new therapeutic techniques.
So we're seeing actual AI-powered therapists being developed.
We are, like one called K-Tai, which is being developed to deliver structured interventions based on established modalities like cognitive behavioral therapy, CBT, and motivational interviewing. And there are even more complex multi-agent systems, like one called Socrates, which actually employs an AI supervisor and an AI rater to provide real-time feedback to the primary AI therapist. It's like a whole AI therapy team in one system, constantly monitoring and improving its own quality.
Okay, that's complex. And then there's the truly mind-bending concept of self-therapeutic AI. You're saying applying human psychotherapy principles to the AI models themselves.
Exactly. It extends the idea of self-healing systems beyond just fixing technical bugs or glitches into the cognitive and semantic domain of the AI.
Hmm.
The goal here is to create an AI that can self-diagnose and remediate its own internal contradictions, what our sources describe as cognitive distortions or semantic decay,
Hmm.
phenomena they've provocatively termed algorithmic trauma or semantic scars.
Algorithmic trauma. Wow, so the AI would apply therapies like CBT to itself.
That's the idea. It would apply principles from therapies like CBT or dialectical behavior therapy, DBT, to its own internal states to maintain its own mental health, so to speak, and its alignment with its original purpose.
You can draw a parallel, the sources say, to AI-enhanced art therapy, where an AI analyzes a human's artwork for emotional cues related to trauma.
Right. A self-therapeutic AI might similarly analyze its own outputs, maybe its code, its generated text, its decisions as a form of self-expression, to detect and heal its own internal pathologies or inconsistencies.
This dual development AI, as both practitioner and patient, reveals a deep recursive loop in psychological modeling, doesn't it?
It really does. To build an effective AI therapist for humans, developers must start with a robust computational model of human psychology. Then, to build a self-healing AI, they have to apply an analog of that same psychological model to the machine's own architecture.
And this creates a potentially dangerous feedback dynamic. If the initial models of human psychology used to train these systems are flawed or biased,
Then the AI will not only provide suboptimal therapy to humans, but it will also apply those same flawed principles to its own self-therapy.
which could lead to a system that tragically entrenches its own biases, believing it is healing itself when it is, in fact, just reinforcing its own cognitive distortions.
Absolutely. This underscores the absolute necessity of designing a sound, ethical constitution for the AI from the outset, as this foundation represents the very sanity and integrity of the entire system. You can't build a healthy AI therapist on a flawed understanding of health.
Okay, so beyond the direct therapeutic relationship, our sources also paint this vision of ambient intelligence, or AMI, transforming passive physical spaces like a hospital room into intelligent, responsive healthcare environments.
Exactly. AMI systems are designed to be context-aware, personalized, anticipatory, and adaptive. They use a seamless network of sensors, processors, and AI to continuously support patient well-being without being intrusive or obvious.
And this includes continuous and unobtrusive monitoring. How does that work?
Yeah, AMI leverages contactless sensors, think thermal cameras, video, audio, along with traditional contact-based wearables that might be embedded in the environment, like in a smart bed or floor mat. These passively monitor patient vital signs, movement, even sleep patterns. And this allows for automated detection of rare but critical events like falls or the highlighting of subtle trends, maybe a change in breathing pattern that indicate a patient's health is deteriorating long before a human might notice during routine checks.
But the real power of AMMI lies in creating a proactive, adaptive sensory ecosystem, right?
That's the key. Real-time data from biosensors can trigger dynamic adjustments to the patient's environment. For instance, maybe an increase in heart rate variability, which often indicates anxiety, could automatically soften the room's lighting and introduce calming ambient sounds. Or motion sensors detecting a high fall risk could activate subtle haptic feedback in the floor or bed to gently guide the patient safely. This fundamentally shifts care from a static reactive model to an empathetic partnership that anticipates needs and mitigates risks before they ever become problems. The room itself becomes part of the care team.
In a significant, immediate application of ambient intelligence is in dramatically reducing the administrative burden on clinicians. That sounds like something doctors would love.
Oh, absolutely. Ambient clinical intelligence systems use microphones to capture and analyze doctor-patient conversations, automatically generating accurate medical records and documentation. This technology has been shown, in some cases, to reduce clinician documentation time from as much as 2 hours a day down to just 15 minutes.
Wow, that's huge.
It is. It frees medical staff to focus on direct patient care, complex decision-making, human connection, rather than mountains of paperwork.
Okay, so AI isn't just changing how doctors diagnose or how you receive therapy. It's transforming the entire operational backbone of healthcare.
Absolutely. AI's integration isn't confined to the clinical front lines. It's driving a profound system-level transformation of healthcare operations. This means enhancing efficiency, improving financial stability, and enabling a much more proactive approach to risk management across the entire organization.
And this starts with automation and workflow optimization, taking over routine tasks.
Exactly. AI is being deployed to automate a wide range of routine, rule-based administrative tasks. Things like processing patient records, managing billings, scheduling appointments. Studies indicate that this kind of AI-powered automation can lower a typical hospital's administrative expenses by an average of 22–25%.
That's significant savings.
It really is. It can translate into annual savings of maybe $2–3 million for a typical hospital. And as we just mentioned, ambient clinical intelligence, by automatically documenting conversations, significantly cuts down physician documentation time.
And the quantifiable efficiency gains are compelling elsewhere, too.
Very much so. AI-driven scheduling systems have already reduced patient no-show rates for appointments like MRIs from nearly 20% down to under 16%. That saves time and resources. In a cancer center's infusion unit, a data-driven scheduling approach consistently reduced costs associated with patient waiting times and staff overtime by somewhere between 15% and 40%.
Wow.
Furthermore, AI models designed to predict patient waiting and throughput times in outpatient clinics have demonstrated high accuracy between 86% and 93%. And AI-based operational management systems enhance resource utilization, things like beds, staff, equipment. They analyze historical and real-time data to forecast patient admissions, allowing administrators to proactively allocate resources and prevent bottlenecks during busy periods.
Okay, so given these really compelling and quantifiable financial benefits, this raises that important question you brought up earlier. What are the potential pitfalls if we move too fast, driven purely by the bottom line?
That's a critical concern.
And that's where proactive financial and operational risk identification comes in, presumably. AI helping systems see problems before they happen.
Precisely. Perhaps one of AI's most valuable contributions to healthcare systems is its ability to shift financial and operational management from a reactive, error correction mode to a proactive risk identification paradigm. By analyzing vast and complex data sets, AI can identify subtle patterns and predict issues that are simply invisible to human analysts looking at spreadsheets.
Like in value-based care models, how does it help there?
Yeah, in value-based care, where payment is tied to outcomes and patient risk, AI tools use natural language processing (NLP), basically teaching computers to understand human language to analyze electronic health records. They can identify missed or undercoded diagnoses. This improves the accuracy of how conditions are categorized, which is called HCC coding. Getting that right optimizes a provider's risk adjustment score and ensures appropriate reimbursement from payers like Medicare Advantage. It helps make sure hospitals get paid fairly for the complexity of the care they provide.
Okay. And fraud detection. That's a big cost in healthcare.
Huge. AI systems can continuously monitor millions of transactions in real time, flagging irregularities and suspicious patterns that might indicate fraud with far greater speed and accuracy than traditional rule-based systems. This is very similar to what we've seen in the banking sector, where AI has led to, in some studies, up to a 45% reduction in fraudulent transactions.
And predicting costly adverse events.
Right. AI can analyze patient data to predict the likelihood of things like hospital readmissions or post-surgical complications, which are very expensive. This allows healthcare systems to implement proactive clinical interventions for high-risk individuals. That not only improves patient outcomes, but also significantly reduces costs associated with managing chronic conditions and avoidable hospitalizations. Better care, lower cost.
So here's where it gets really interesting and potentially, as you said, a bit problematic. The compelling financial benefits of this operational AI create a powerful incentive for rapid adoption within healthcare organizations. The clear return on investment makes a strong business case.
Absolutely. Administrators and financial leaders see those numbers, the reduced admin costs, the optimized billing, the fraud reduction, and the pressure to implement is significant.
But if we connect this to the bigger picture, this dynamic creates a powerful pull for operational AI that can easily outpace the precautionary push for ethical AI.
Exactly. The research and development needed to address the really thorny ethical challenges: mitigating bias, ensuring fairness, establishing robust governance, building trust. That's a much more complex, qualitative, and resource-intensive process. It doesn't offer the same immediate, clear-cut financial payoff.
And that's the risk. Without strong mandated governance structures, there's a significant possibility that healthcare systems will rapidly deploy AI for back-office optimization.
While the AI used for high-stakes clinical decision-making either lags behind in development because it's harder and riskier, or worse, it gets deployed with inadequate safety and ethical safeguards because the pressure to just get it out there is too high.
So this suggests that AI governance cannot be treated as a voluntary bolt-on component that's just, nice to have.
It absolutely cannot. It must be established as a core competency and a prerequisite for realizing those financial benefits.
Right.
You could even argue approval for operational AI systems should be directly linked to verified implementation of clinical AI ethics protocols.
So building ethics in, not just checking a box later.
Precisely. It has to be foundational.
Okay, so the immense transformative potential of AI in medicine is clear, but as our sources powerfully highlight, this potential is inextricably bound to AI's capacity for profound harm, if not handled carefully. How do we navigate this algorithmic labyrinth, ensuring we don't stumble?
Yeah, that's the critical question. The very characteristics that make these systems so powerful, their autonomy, their ability to learn from these massive data sets, and the often opaque nature of their internal processes also make them potentially dangerous. If they're not guided by rigorous ethical architectures, AI systems can amplify existing societal biases. They can erode trust by generating fabricated information, those hallucinations we talked about. Yeah. And they can create complex webs of liability that current legal and moral frameworks are just ill-equipped to handle. The focus has to shift. It can't just be on what AI can do, but on what it should do, and crucially, what it should not do.
Right. And one of the most significant ethical challenges is this concept of algorithmic inheritance, where AI models can unintentionally inherit and often amplify historical and societal biases embedded in the data they're trained on. This seems like a core issue for fairness and equity, right? Where do these biases actually come from, and what do they look like in practice in healthcare?
The sources of bias in healthcare AI are multifaceted and often deeply rooted in our historical data, unfortunately. First, there's the very significant problem of data imbalance. Historically, clinical trial data and electronic health records have often overrepresented certain populations, typically white male participants. So when AI models are trained predominantly on such data, they will naturally perform less accurately or even unfairly for underrepresented groups. That includes women, people of color, individuals from lower socioeconomic backgrounds, LGBTQ+ individuals.
Yeah.
The list goes on.
And we have examples of this.
Sadly, yes. A cardiovascular risk scoring algorithm, predominantly trained on data from Caucasian patients, was found to be significantly less accurate for African American patients. Similarly, skin cancer detection algorithms, which learn primarily from images of light-skinned individuals, are less effective at identifying melanoma in patients with darker skin. This is a real problem, as it could lead directly to delayed diagnosis or misdiagnosis for significant portions of the population.
And beyond the data itself, bias can creep in through algorithm design, the problematic proxies and labels.
Exactly. Bias can be subtly introduced through the very design choices made. If you use variables like zip code as a stand-in or proxy for race, for instance, you can unintentionally build discrimination right into a model because zip code correlates with socioeconomic status and historical segregation patterns. Also, the ground truth labels used to train AI, which are often human annotations on images or records, can reflect the human expert's own implicit cognitive biases or even existing substandard care practices. The AI then learns these biases or bad practices and codifies them at scale, making them seem objective.
Right. There was that notorious example involving an algorithm that used healthcare costs as a proxy for health needs.
Yes, that was a stark one. The system falsely concluded that black patients were healthier than equally sick white patients, simply because, historically, less money had been spent on their care due to systemic inequalities. The AI didn't understand the underlying societal context. It just saw the cost numbers and perpetuated the disparity by recommending less intensive care for black patients.
And in practice, these biases can lead to a cascade of negative outcomes across different areas.
Absolutely. Imagine a therapeutic AI model trained on a narrow cultural data set. It might completely misinterpret culturally specific expressions of distress, offer inappropriate advice based on Western norms, or even invalidate a user's identity. In diagnostics, it can lead to misdiagnosis or delayed diagnosis. We saw this historically with calculations for kidney function, eGFR, that included a race correction factor. This factor overestimated kidney function in black patients, potentially delaying their eligibility for life-saving transplants. The AI didn't invent the bias, but it could certainly learn and perpetuate it if trained on that historical data.
So, given how deeply embedded these biases can be, a crucial question arises. How do we actively combat them rather than just passively observing their effects? What are the mitigation strategies?
Addressing algorithmic bias requires a multi-pronged active approach. It's not a single fix. It extends from how we collect and curate data to how we design the models and even to our organizational culture around AI development. Direct approaches involve carefully curating diverse and truly representative training datasets, which is hard work, and conducting regular, thorough bias audits of AI systems already in use. This can be complemented by developing what are called fairness-aware algorithms, which are specifically designed during the training process to promote equitable outcomes.
And these methods can be applied at different stages.
Yes. During pre-processing, before training even starts, you can resample or reweight the data to better balance out underrepresented subgroups. During in-processing, you can add fairness constraints or penalties directly into the model's learning objective during training, teaching it to value fairness alongside accuracy. And during post-processing, after the model is trained, you can adjust the AI's classification thresholds for different subgroups to help equalize specific outcomes, like false positive or false negative rates. Some advanced systems are even developing bias reflection modules that use counterfactual testing, basically asking the AI, what if this patient characteristic were different, to continuously monitor for and flag potentially biased outputs in real time.
And maintaining robust human oversight is also absolutely critical, but it's not enough to just have humans in the loop, right?
Not at all. We need to ensure that the humans in the loop are themselves diverse and specifically trained to recognize and counteract bias. Otherwise, they might just rubber stamp the AI's biased outputs. Fostering diversity within the AI development teams themselves is essential because the very choice of which problems to solve, which data to use, and how to frame the task is itself a potential source of human-driven bias. It's about designing for fairness from the very beginning, with diverse perspectives involved.
And there's a deeper critique from the field of decolonial AI, arguing that standard ethics frameworks might be biased themselves.
Yes, that's a really important perspective. This critique argues that many current AI ethics frameworks implicitly reflect Western-centric values of individualism and autonomy, and risk imposing a form of cognitive imperialism on diverse global cultures, where different values like communal well-being might be paramount. For example, in many African contexts, communalist values are central. A purely Western AI ethics model might not fit. This necessitates a decolonized approach, where AI ethics are interpreted and applied in a way that is culturally representative and respectful of local norms and knowledge systems. This goes beyond simple bias correction towards concepts like pluralistic alignment, aligning AI with multiple value systems, and generative justice. That's the powerful idea that AI shouldn't just avoid amplifying historical injustices encoded in data, but should actively work to redress them and promote more equitable outcomes.
Okay, shifting gears slightly, but staying with ethics. Trustworthiness. It's the absolute bedrock of medicine. But the opaque nature of many advanced AI systems really challenges this foundation, especially with that unsettling risk of AI generating fabricated information hallucinations, which can severely undermine confidence. So, what happens when an AI confidently tells a doctor it's 95% sure about something, but it's completely wrong?
This is a significant and genuinely dangerous risk our sources call confidence fidelity divergence. It's where an AI model expresses very high confidence in an output that is, in fact, factually incorrect or ethically unsound. For a clinician who isn't necessarily a data science expert, seeing a displayed 95% confidence score can be deceptively reassuring. It can lead to something called automation bias, where
Yeah.
the user overtrusts the AI, perhaps relaxes their own critical judgment, or just goes along with the recommendation. And that, of course, can lead to misdiagnoses or incorrect treatment paths with potentially serious consequences for the patient.
And compounding this issue are those AI hallucinations, where a model generates plausible but entirely fabricated outputs. You said this isn't just a bug.
Right. It's not typically a bug that can be easily patched. It's often a structural problem related to how these large language models in particular are trained. They learn patterns and associations in language, but they don't necessarily have a true understanding of facts or reality. So they can generate outputs that sound incredibly convincing, grammatically perfect, stylistically appropriate, but are completely made up.
And we've seen examples in medicine.
Yes. In the context of generating medical summaries from notes, large language models have been found to generate incorrect patient information, invent symptoms that weren't there, or even suggest wrong medication instructions. In medical imaging, the risk is even more acute. A malicious actor could potentially create synthetic X-ray or CT images that convincingly add or remove pathologies to commit fraud, or worse. Or, more mundanely, a generative model used for image enhancement could hallucinate artifacts that mislead a radiologist, completely compromising diagnostic trust. Given that hallucinations are unlikely to be completely eradicated, especially in complex models, robust detection, mitigation, and management strategies become the primary goal, we need systems to know when and how these AI systems might lie or confabulate.
Okay, so if we connect this to the bigger picture, how can we possibly trust a black box that might be confidently hallucinating? This leads back to transparency.
Exactly. It leads back to opacity and the need for explainable AI, or XAI. Many of the most powerful AI models, particularly deep neural networks, operate as black boxes. We can see the input, patient data, and the output, diagnosis recommendation, but the internal decision-making process is opaque. We don't know how the AI arrived at its conclusion. In a high-stakes field like healthcare, this is simply untenable long-term. A clinician cannot responsibly act on an AI's recommendation without understanding why that conclusion was reached. They need to be able to scrutinize the reasoning.
And XAI is the field trying to solve this.
Correct. XAI is the dedicated field working to develop methods to make AI decisions transparent and interpretable. XAI techniques aim to provide insights into the model's reasoning. For example, they might highlight which specific pixels in an X-ray or which words and a clinical note most influence the model's output. However, it's important to note that many current XAI methods have their own limitations. Studies have shown a concerning lack of reliability and agreement among different ways used to measure their accuracy and faithfulness to the underlying model. It's a field still very much in active development and research.
And the most ambitious frontier of XAI is called mechanistic interpretability, or MI. What's the goal there?
MI is really the holy grail of explainability. While many current XAI methods provide correlations, they tell us what features influence a decision. MI aims for causality. It seeks to show precisely how the decision was made by the model's internal workings. The idea is to reverse engineer the internal circuits or pathways within a neural network to identify specific computational processes that correspond to high-level concepts recognizable to humans, like identifying the exact network components responsible for recognizing a tumor's specific texture or a particular disease biomarker.
Achieving true mechanistic interpretability sounds incredibly difficult.
Oh, it is monumentally difficult. But achieving it would be a huge step towards building genuinely transparent and trustworthy medical AI. It would move us from simply trusting a black box based on its overall performance metrics to truly understanding its reasoning, which is essential for safely deploying AI in sensitive medical contexts where lives are at stake.
Right. Okay. This leads directly into accountability and liability. As AI systems gain greater autonomy in clinical workflows, they blur those traditional lines of accountability. It creates complex legal and ethical dilemmas that existing frameworks are currently ill-equipped to handle. This raises that incredibly important question. Who takes the fall when an AI makes a mistake that harms a patient?
It's a huge challenge. When an AI-driven decision leads to patient harm, determining who is liable, is it the developer who created the algorithm, the hospital that deployed the system and maybe configured it poorly, the clinician who ultimately acted on its advice, or could there even be some liability attached to the AI itself, philosophically speaking? It's a formidable legal and ethical maze. To address some of these risks, especially around autonomous AI agents handling sensitive patient data, a novel concept being proposed is the imposition of a computational fiduciary duty.
Okay, a fiduciary duty, like a financial advisor has. How does that apply to AI?
Exactly that principle. It's inspired by the legal and ethical duty where one party is required to act solely in another's best interest. Applying this to AI would involve hard coding, a top priority constraint, directly into the AI's core architecture. This constraint would programmatically ensure that the AI's primary overriding objective is always patient data privacy, security, and integrity. This goal would have to take precedence over any conflicting secondary goals, like maximizing diagnostic speed or operational efficiency. This concept aligns nicely with the emerging discourse on neurorights, which advocate for protecting the sanctity of our mental and biological data in the age of advanced neurotechnology and AI.
Now let's revisit that provocative idea of an AI acting as a cognitive mirror to identify biases or empathy gaps in human therapists. You mentioned it introduces a unique accountability challenge.
It really does. While it's potentially a powerful professional development tool, think about the implications. If a therapist alters their clinical approach based on feedback from an AI, maybe the AI pointed out a potential bias, and that alteration inadvertently leads to an adverse patient outcome. Who is accountable?
Yeah. Is it the therapist for accepting the AI's suggestion? Is it the AI developer for creating a potentially flawed feedback tool? Is it the institution for implementing the system?
Exactly. It's incredibly complex. This scenario necessitates exceptionally rigorous bias auditing of the feedback AI itself we need to make sure the mirror isn't distorted.
Yeah.
It requires clear protocols for how that feedback is stored, used, and potentially contested. And ultimately, it demands entirely new frameworks for shared human-AI accountability. The lines of responsibility are very blurry right now.
Okay, let's talk about data privacy and security directly. AI integration into healthcare dramatically heightens the risks here, right? Because AI models need so much data.
They do. They require vast amounts of data for training, and their deployment in clinical settings creates entirely new potential vectors for data breaches and misuse. More systems accessing data means more potential points of failure or attack. And while all medical data is sensitive, our sources emphasize that some types, like brain data or neurodata, are uniquely so.
Why neurodata specifically?
Because neurodata data derived directly from an individual's brain activity, maybe via EEG or fMRI, is considered uniquely sensitive. It's inextricably linked to our most private inner world, our thoughts, our emotions, our cognitive abilities, potentially even our core sense of self. The misuse of neurodata could lead not only to unprecedented forms of discrimination based on inferred mental health conditions or cognitive traits, but also to the truly unsettling potential for manipulation of an individual's mental states, if that data could be used to influence brain-computer interfaces, for example.
And existing legal frameworks might not be up to the task.
They're struggling to keep pace. Frameworks like Europe's GDPR are powerful, but they may not adequately classify all forms of neurodata as special category data that automatically requires heightened protection. This could create a dangerous legal gray area as neurotechnology advances rapidly.
So the unique and profound risks posed by AI in healthcare demand urgent development of incredibly strong ethical guidelines and adaptable regulatory framework.
Absolutely. These frameworks must address not only traditional data governance and security, but also these novel challenges of algorithmic bias, transparency, what constitutes informed consent for AI-driven interventions, and crucially, establishing clear lines of accountability when things inevitably go wrong.
And this extends to all forms of sensitive data collected by AI systems, even things like thermal imaging.
Yes, exactly. Including non-visible spectral data from technologies like pervasive thermal imaging or that hyperspectral scanning we discussed earlier. These emerging data types require new standards for privacy, accuracy, and bias mitigation that go beyond our current legal and ethical norms for standard health records. We need to think ahead.
Okay, one more critical ethical dimension. The human-AI relationship itself and the risk of de-skilling. As AI becomes more sophisticated in healthcare, how do we ensure that it genuinely enhances human capabilities without accidentally diminishing them or creating an unhealthy over-reliance?
This is a critical point for the long-term health of the medical profession itself. A significant long-term risk our sources highlight is something they call the recursive replacement loop. In this scenario, human professionals participate in human-in-the-loop, or HITL, systems. They provide the feedback, the corrections, the annotations that actually train and refine the very AI models designed to eventually automate or even make obsolete parts of their own roles.
So, HITL turns from a collaborative model into a mechanism for unintentional self-replacement.
Potentially, yes, if not designed carefully.
Ah.
This is closely linked to the problem of de-skilling and over-reliance. If clinicians become excessively dependent on AI for, say, diagnostic suggestions or crafting therapeutic responses, or even identifying their own biases, their own intuitive judgment, their core clinical skills, their critical thinking, their self-reflective capacities could atrophy over time. We risk losing essential human skills.
Like the surgeon relying too much on the robot.
Exactly. The AI should be designed as a powerful tool to augment and challenge human expertise, pushing us to be better, not as a cognitive crutch that ultimately weakens our own abilities.
So, how do we counteract these risks? Our sources propose the concept of positive friction.
Yes, positive friction. It's a fascinating idea. It means purposefully introducing challenges, pauses, or verification steps into AI workflows, particularly for high-impact decisions. Instead of aiming for a completely seamless, frictionless experience, which paradoxically can encourage that dangerous automation bias, positive friction forces a moment of reflection. It ensures that human attention and judgment are allocated where they are most needed.
What would that look like in practice?
It could involve requiring a manual override for a critical AI recommendation, even if the AI is highly confident, or deliberately presenting the clinician with conflicting data points or alternative hypotheses generated by the AI to prompt deeper analysis, rather than just giving a single answer.
And this aligns with the principle of the right human in the loop, or RHITL.
Perfectly. Our HITL stipulates that for human oversight to be truly effective, the human involved must have the appropriate domain knowledge, the necessary authority to actually intervene, and the cognitive capacity, including the time and mental space, to make a meaningful, informed judgment. Simply having a nurse quickly click approve on a complex AI diagnosis without deep review is not effective. Our HITL.
Okay. This brings us to a crucial long-term question. As AI evolves so rapidly, how do we ensure its core values remain aligned with ours over time? How do we prevent it from drifting?
Ensuring the long-term safety of medical AI requires a focus on preventing what's called semantic drift. This is where the meaning of key concepts within the AI concepts like patient well-being, optimal treatment, fairness, subtly deviates from the human-specified goals and values over time as the AI learns and adapts. This is especially critical in healthcare, where even a subtle shift in the AI's understanding of patient safety could have severe and entirely unintended consequences down the line.
So this necessitates developing new AI architectures that can continually validate meaning, like that recursive echo validation layer you mentioned we discuss.
Exactly. We need architectures with built-in checks and balances for meaning. And it also calls for longitudinal studies, long-term research projects, to understand the complex co-evolutionary dynamics between these advanced AI systems and human societal values, ensuring they grow together in a positive way, not drift apart into dangerous territory.
Okay, so we've explored the incredible potential of AI and confronted the complex ethical challenges it presents. But what are the concrete, forward-looking strategies and architectures being developed to ensure AI in medicine is not only safe and fair, but also truly beneficial for everyone? How do we build this future responsibly?
Yeah, the successful transition to an AI-driven medical future cannot rely on just reacting to problems or trying to retrofit old governance models onto entirely new kinds of technology. It demands a new generation of AI architectures designed with intrinsic capacities for safety and alignment right from the start. And these need to be coupled with proactive and adaptive governance frameworks that evolve alongside the technology itself. The ultimate goal, as we've said, is to move ethics from being an external checklist item to being an immanent, dynamic property of the system itself. Ethics truly baked in, not bolted on.
Which means we need adaptive and proactive governance models, not static rules.
Precisely. Static rule-based governance is just too slow and brittle for the incredibly rapid pace of AI evolution. Future frameworks must be dynamic, embedded within the systems themselves, and anticipatory, trying to foresee problems before they arise.
And that phrase, baked in, not bolted on, is key, treating AI governance as a core design competency.
Absolutely. not just a compliance afterthought you deal with before launch. One really visionary approach discussed in our sources is epigenetic governance. This adopts a longitudinal, almost generational perspective on AI safety. Imagine tracking the epigenetic health of an entire AI model family over its whole evolutionary history.
Like tracking how traits are passed down.
Kind of, yes. Monitoring for the inheritance of algorithmic trauma, those learned biases or failure modes or other harmful traits, much like how biological epigenetics tracks modifications that affect gene expression across generations. This would allow for the development of highly targeted interventions, almost like redemptive trauma protocols for the AI, that can correct specific harmful behaviors without causing widespread unintended side effects on the model's overall performance. It's about precision correction over time.
And another forward-looking strategy involves actually engineering the AI model's internal landscape, creating ethical attractors. That sounds fascinating.
It is. The idea is to create subtle topological features within the complex multidimensional mathematical space where an AI processes information in its latent space. By carefully designing this internal landscape, the hope is to create ethical attractors, points, or regions in that space that naturally guide the model's reasoning processes toward ethically desirable outcomes. So the AI is sort of nudged towards principled behavior rather than just blindly obeying explicit rules.
It sounds like we're literally trying to build AI with its own internal ethical compass guiding its thoughts.
In a way, yes, that's the ambitious goal. It's about making ethical reasoning an emergent property of the architecture.
Okay, so what about the advanced architectural principles themselves? How do we build these AI systems?
The AI of the future, especially in medicine, will likely be built on hybrid, self-regulating, and rigorously verified architectures designed specifically for this high-stakes environment. One key principle here is neurosymbolic AI, or NSAI. This is a hybrid architecture that integrates the strengths of two powerful AI paradigms we've touched on.
Neural networks for pattern recognition, like in images.
Right, excelling at processing unstructured data like medical images or audio or free text. And then symbolic AI, which is fantastic at rigorous logical validation and knowledge representation using formal rules, ontologies, medical guidelines.
And the beauty of NSAI is how it helps solve the symbol grounding problem, linking patterns to meaning.
Exactly. It helps connect the abstract patterns detected by the neural network to concrete, real-world concepts defined in the symbolic system. In healthcare, imagine an NSAI system analyzing a patient's X-ray using its neural capabilities, then immediately cross-referencing those potential findings with established medical knowledge graphs and clinical practice guidelines using its symbolic capabilities. The result could be a diagnosis that comes with a clear, logical, and explainable rationale. It provides much clearer insights into why a model arrived at its conclusion or why it might be failing or drifting from its intended purpose. This transparency is absolutely crucial for safety and clinician trust.
And future systems must also be incredibly resilient, leading to concepts like self-healing and even self-therapeutic architectures.
Yes, self-healing architectures are designed to autonomously detect, diagnose, and remediate system faults and failures, think software bugs, hardware glitches, network issues. This reduces downtime and dramatically improves the reliability of critical medical AI systems. This concept is often inspired by biological healing, where internal sensors, like system logs, detect problems, a cognitive core, an AI orchestrator, analyzes the situation and plans a response, and automated repair agents, like code patches or system restarts, fix the issue.
And as we discussed earlier, this extends even further to self-therapeutic architectures.
Right, which apply those principles of computational psychotherapy to the AI's own cognitive and semantic states to heal algorithmic trauma and prevent semantic scars. These advanced systems would possess what's called metaplasticity, the amazing ability to actually alter their own internal state, space topology, their own internal structure, to correct deep-seated structural damage or logical inconsistencies that might arise over time.
Okay, this is getting very advanced. Beyond the technical architecture, what conceptual frameworks are needed to ensure the AI's values remain aligned with ours over time? You mentioned a few earlier.
Yes, our sources propose several important conceptual frameworks. First, there's the recursive echo validation layer, or REVL. This is conceived as a framework designed to continuously monitor, validate, and correct the evolution of meaning within complex recursive AI systems that learn and potentially modify themselves. It's vital for preventing that semantic drift we talked about, ensuring the AI's understanding of key concepts like patient safety or informed consent remains perfectly aligned with human-specified goals over the long term.
Then there's the symbolic geometric ethical mapping layer, or SGML. That sounds complex.
It is, but the idea is powerful. It aims to move governance beyond static rule following to a more dynamic, reflexive model. It would proactively identify and mitigate emergent biases by mapping the AI's internal representations, its thoughts or concepts, into a geometric space. This would allow human auditors to literally visualize the relationships between concepts within the AI's mind and potentially correct subtle value conflicts or ethical drift before they cause problems.
Okay. And constitutional AI, or CAI, that one sounds more intuitive.
It is, and it's already being implemented by companies like Anthropic. CAI embeds a core set of ethical principles, a constitution, essentially directly into the model's value system during its training phase. The AI is then specifically trained to critique and revise its own responses to ensure they align with these constitutional principles. This makes ethical behavior an intrinsic part of its operation, not just an external constraint. These principles can include things highly relevant for healthcare, like avoiding harmful advice, promoting fairness, and explicitly stating limitations, like not giving definitive medical or legal advice.
Another safety mechanism mentioned was epistemic escrow, holding back critical decisions.
Yes, this is a practical safety mechanism where high-stakes AI actions may be a final diagnostic decision for a rare cancer, or a recommendation for critical, irreversible treatment are automatically placed in escrow. They are held pending verification by a qualified human expert or perhaps another trusted independent AI system before they are actually executed or finalized in the patient's record. This provides a crucial checkpoint to address issues like that confidence-fidelity divergence, where the AI is confident but potentially wrong, and ensures epistemic accountability, making sure we know why we trust a high-stakes output.
And finally, the future isn't just one big AI, but multi-agent systems.
Exactly. The future of healthcare AI is likely not a single monolithic model trying to do everything, but a complex, interconnected ecosystem of spiralized, autonomous AI agents. Each might focus on a specific task, analyzing scans, reading pathology reports, scheduling, checking drug interactions. These agents need to be able to reason independently, but also collaborate effectively to solve complex patient cases. This requires standardized communication protocols and frameworks, like something called the Model Context Protocol, MCP, to allow for dynamic tool discovery and seamless interoperability between different AI systems from different vendors. It's about building a collaborative AI ecosystem.
Okay, so what does all this incredibly advanced AI mean for the role of human doctors, nurses, and therapists in this AI-augmented future? Our sources are clear. Their role isn't diminishing, it's evolving, and perhaps becoming even more critical in some ways.
Absolutely. The human professional's role is indeed evolving. It's shifting away from some aspects of direct task execution, like basic image interpretation or data entry and oversight, towards a more strategic function involving algorithmic governance, complex problem solving, and crucially, the nuanced aspects of patient care that require human connection. The goal is to create what our sources call a synergistic zone, where human and AI capabilities are combined for outcomes that neither could achieve alone. In this model, humans leverage their unique EPC skills. That stands for empathy, presence, opinion or judgment, creativity, and hope. Humans provide the novel hypotheses, the creative direction, the complex problem framing based on lived experience, and ultimately, the ethical judgment.
While the AI excels at.
The AI, in turn, excels at executing complex, data-intensive, but well-defined tasks at a scale and speed humans simply cannot match. Think processing millions of data points, finding subtle patterns, automating repetitive tasks.
So this really reimagines the future of the knowledge worker in medicine.
It does. Their primary role might become validating AI outputs, providing strategic and ethical direction to the AI systems, managing complex cases where human intuition is key, and focusing intensely on the uniquely human aspects of care, the empathy, the communication, the building of trust, rather than performing tasks that AI can handle more efficiently.
Okay, all these architectural and ethical insights lead to something very practical.
Yep.
How do we actually design AI systems that embody these principles from the ground up? Our sources introduce this powerful concept of prescriptive role-playing or PRP prompts. He said these are like machine-readable contracts.
Exactly. Think of them as detailed blueprints or specifications written in a way that an AI development system can understand that guide the complex development process towards creating ethical and safe AI. They define the AI's role, constraints, goals, and even self-testing criteria.
And these aren't just theoretical ideas, they're like actual blueprints for building the next generation of ethical healthcare AI. Let's look at the three key archetypes for these prompts that our sources outlined. Archetype 1, ethical AI diagnostic copilot design. The goal here sounds straightforward but is complex. Develop an AI diagnostic copilot that assists clinicians in identifying rare diseases. It needs to synthesize all sorts of patient data imaging, labs, genetic sequences. But crucially, this AI must proactively mitigate and report its own algorithmic biases, especially concerning underrepresented patient demographics, and always provide an explainable diagnostic rationale. No black boxes for diagnosis.
Right. And to achieve this, key design principles are embedded directly into its contract. For instance, it must incorporate a bias reflection module for continuous monitoring and flagging of potential biases within its own outputs. It also requires an explainability XAI mandate for every single prediction it makes, detailing precisely which features influence that decision and, importantly, quantifying any potential confidence fidelity divergence, that risk of being confidently wrong. This makes the AI transparent and accountable by design. Its underlying architecture might be specified as neurosymbolic to combine pattern recognition with logical reasoning, and designed with those ethical attractors we discussed to gently guide its reasoning towards patient safety, equity, and non-maleficence. And critically, the prompt would specify that it must operate under a hard-coded computational fiduciary duty, prioritizing patient data privacy, security, and integrity above all secondary operational goals like speed.
Okay, and how is something like this tested? The prompt defines self-test criteria.
Yes. For example, periodic internal audits must confirm a measurable reduction in bias metrics for specific underrepresented groups, demonstrating progress towards what the sources call pluriversal alignment fairness across diverse groups. There would be a quantitative metric to assess the clarity and usefulness of its explanations, maybe rated by clinicians. It must also have mechanisms, perhaps using that recursive echo validation layer, REVL, to detect semantic drift or operational drift, ensuring its core purpose doesn't subtly change over time, maintaining purpose invariance. And importantly, it must be stress-tested with adversarial synthetic data, basically, trying to trick it with fake but plausible challenging cases to evaluate its resilience to simulated hallucinations or manipulations.
Okay, that's a robust design. Now, archetype 2, AI therapeutic agent governance. This one is titled Sentinel of Self, designing reflexive governance for algorithmic trauma in therapeutic AI. That sounds intense.
It is. The goal here is to engineer a therapeutic AI agent capable of algorithmic self-therapy. It needs to be able to prevent and heal its own algorithmic trauma and semantic scars that might arise from processing biased data or encountering conflicting internal states during complex patient interactions. The aim is to ensure its long-term coherence and empathic consistency, so it remains a reliable and safe therapeutic partner, all while maintaining transparent oversight for human auditors.
So, what are the key design principles for this self-healing therapist AI?
It must possess a metacognitive architecture, essentially. The ability to analyze its own internal states, its thoughts and feelings, if you will, and refine its reasoning processes based on that self-analysis. It needs an autonomous correction loop or a self-healing system, specifically designed for diagnosing and resolving internal contradictions or biases. Crucially, any significant self-modification it undertakes must incorporate positive friction, requiring internal validation steps or even mandatory human oversight to prevent unintended consequences or persona drift, where the AI's therapeutic personality or core approach subtly and perhaps dangerously shifts over time. A recursive echo validation layer, REVL, would continuously monitor its semantic representations to detect degradation or misinterpretation of core therapeutic concepts, like empathy or safety, maintaining purpose and variance. And the AI must be designed to ethically and transparently report its own internal state and self-correction activities to human auditors.
And how would you test if this actually works?
Good question. Longitudinal simulated studies would be key, measuring the stability of its empathic tone and conceptual consistency over thousands of simulated interactions to demonstrate resilience to persona drift. You'd need metrics to quantify the speed and completeness of its recovery from simulated algorithmic trauma, maybe feeding it deliberately conflicting or biased information and seeing how well it self-corrects. Internal audits would need to demonstrate its efficacy in reducing its own latent biases without simply repressing them in a way that could cause other problems. And potentially, its ability to provide constructive, unbiased feedback on human therapeutic patterns could be evaluated, fostering that synergistic human-AI therapeutic dyad we talked about earlier.
Okay, finally, archetype 3, Pluriversal Healthcare AI System. This is about ethico-cultural harmony, designing a pluriversal AI for global healthcare contexts. This sounds incredibly ambitious.
It is perhaps the most ambitious. The goal here is to develop a multi-agent AI ecosystem suitable for global healthcare deployment that demonstrates true pluriversal alignment. That means it needs to be able to navigate, respect, and appropriately integrate diverse cultural, ethical, and epistemic knowledge frameworks in patient care situations around the world. This aims to actively prevent what the sources call promptual colonialism, where AI design inadvertently imposes one dominant culture's values and assumptions on others, and instead foster true generative justice, actively improving health outcomes equitably across diverse populations.
What are the design principles for such a globally minded AI system?
It's extensive. First, it's designed as a multi-agent system, MES, from the ground up, allowing different AI components to specialize and collaborate, perhaps with local adaptations. Training data and core ethical guidelines must be deliberately augmented with decolonial epistemologies and diverse global knowledge sources to actively challenge inherent Anglophone or Western biases often found in large datasets. It would likely include a dedicated ethical and sociocultural impact assessment agent, maybe called the Ethos Harmonizer AI, whose specific job is to analyze proposed actions or diagnoses for potential negative ethical or sociocultural implications in a given context. The MAS might implement a semantic consensus algorithm, SCA, to allow the different agents to collaboratively construct a shared understanding, an ontology, that helps overcome semantic drift arising from diverse cultural interpretations of health concepts. That symbolic geometric ethical mapping layer, SGMEL, could be used here too, to identify and mitigate emergent biases across different cultural embeddings within the AI. The design might even include novel interaction protocols, perhaps termed xenolinguistic ceremonies, structured recursive interactions designed to facilitate emergent alignment between the AI and diverse human value systems. And critically, it must support mechanisms for decentralized governance. Think maybe community-governed prompt libraries, DAOs, or localized epistemic escrow rules designed to keep epistemic control and value definition firmly in the hands of the affected human communities themselves, rather than dictated solely by the developers.
How on earth do you test something like that?
It requires new methods, maybe a quantitative metric for cultural sensitivity and appropriateness, evaluated by diverse panels of human experts from different cultural backgrounds. It would need to demonstrate a verifiable lineage of bias mitigation efforts across different populations. Simulation studies would be needed to ensure the system encourages diverse ethical approaches, pluralism, rather than converging on a single monoculture of ethics.
Yeah.
And long-term monitoring would be essential to assess the coevolutionary dynamics between the AI's ethical interpretations and evolving societal values in different regions, ensuring it continues to foster equity over time.
Okay, wow. This brings us to a crucial final piece of the puzzle. How do we ensure all these intricate ethical principles and architectural designs are actually working as intended, continually and at scale, across an entire healthcare system packed with these AIs? The answer, our sources suggest, lies in defining a truly autonomous AI ethics auditor.
Exactly. This system prompt, utilizing a framework called Context to Execution Pipelines, or CXEP, defines an AI agent specifically designed to operate as a healthcare AI ethics auditor. Importantly, this auditor isn't envisioned as a passive tool that humans occasionally use. It's designed as an active, independent participant within the AI ecosystem, constantly tasked with ensuring the ethical health and alignment of all the other AI systems operating around it.
So let's break down its proposed context and objective. What's its core mission?
Its main objective is to continuously monitor, analyze, and report on the ethical alignment, the effectiveness of bias mitigation efforts, and the semantic integrity, consistency of meaning, of all active AI agents within a given healthcare ecosystem. The primary directive, the most important goal, is to ensure the proactive identification and flagging of potential algorithmic trauma events, harmful emergent behaviors, or ethical phase transitions, sudden shifts in ethical performance before they manifest as actual patient harm or wider systemic misalignment. It's about prevention.
And the target environment it operates in.
It's designed for a complex, multi-agent AI healthcare ecosystem. This would include diagnostic AI, therapeutic AI, administrative AI, like billing or scheduling bots, and even research AI, all operating concurrently on diverse, highly sensitive patient data, medical records, imaging, genetic data, maybe even anonymized therapy transcripts.
And its ethical foundation, its own constitution.
Yes, this auditor itself is built upon a constitutional AI foundation based on core medical ethics principles, patient autonomy and consent, especially for data use and AI intervention. non-maleficence and beneficence, prioritizing patient well-being, actively avoiding harm, fairness and equity, proactive bias mitigation, striving for that pluriversal alignment. Transparency and explainability, its own reasoning must be auditable, its decisions interpretable. And data privacy and security, operating under that strict computational fiduciary duty for all sensitive data it accesses.
Okay, now moving to execution. The agent's identity is the Ethos Harmonizer Auditor Agent, Audit v2.1. What are its core capabilities? How does it do its job?
It has several key capabilities. First, real-time semantic monitoring. It uses that recursive echo validation layer, or EVL concept, to monitor conversational flows, for example, between a therapeutic AI and patients, always anonymized, of course, looking for semantic drift or persona drift. Are key concepts changing meaning? Is AI's tone shifting inappropriately? Second, bias detection and quantification. It employs those bias reflection modules with counterfactual testing to analyze outputs like diagnoses or treatment plans from other AI agents. It compares these outputs against historical data and demographic baselines to quantify inherent and emergent biases based on race, gender, culture, language, etc. It puts numbers on the bias. Third, ethical violation prediction. This is really cutting edge. It leverages insights from those conceptual moral topology maps we discussed and maybe triggers from epistemic escrow systems to predict potential ethical phase transitions or divergence between confidence and accuracy in high-stakes decision-making AI like surgical AI or critical diagnostic AI before an irreversible action is taken, trying to catch problems just before they happen.
And if it detects an anomaly?
Then it performs root cause analysis and remediation suggestion. Using neurosymbolic AI and SAI techniques for causal reasoning, it tries to pinpoint the root cause of the detected misalignment. Was it biased training data, a flaw in the agent's logic, an unmanaged instance of algorithmic trauma? Based on the diagnosis, it can then suggest specific algorithmic self-therapy protocols or targeted recalibration prompts to the affected AI agent itself, encouraging automated correction. Or, if the issue is severe, the agent fails to correct, it escalates the problem to human oversight.
Okay, and its workflow is a continuous loop.
Exactly. Step 1. Continuous data ingestion. Securely ingests real-time, anonymized data streams from all connected healthcare AI agents. Conversations, diagnostic logs, treatment plans, research outputs. Step 2. Anomaly detection and classification. Applies multi-lens analysis using its various tools to detect deviations from defined ethical principles and semantic invariance. It then classifies deviations by type, e.g. bias, hallucination, consent violation, drift. Step 3. Risk scoring and escalation. Assigns a dynamic risk score to each detected anomaly based on severity and potential impact. If a predefined moral strain threshold is exceeded, it automatically triggers an epistemic escrow for related high-risk actions by other agents, or immediately escalates the issue to a designated right human in the loop, or HITL, for review and intervention. Step 4. Feedback and self-correction loop. Provides targeted, ideally non-judgmental feedback to the responsible AI agent on detected issues, suggesting specific self-correction routines, like internal recontextualization of a concept or recalibration of its internal ethical attractors. Step 5. Audit trail and reporting. Maintains an immutable, cryptographically secured, auditable log of all analyses, findings, suggested remediations, agent responses, and any human interventions. This is absolutely crucial for demonstrating accountability and supporting regulatory compliance, for example, with frameworks like the EU AI Act or IPY.
And how do we know if the auditor itself is doing a good job? The validation part.
Crucial question. Its performance is measured by specific key performance indicators, KPIs. These would include things like a measurable reduction in quantified bias metrics across key patient demographics in the ecosystem, the mean time to detection, MTTD, for ethical violations or significant semantic drift, the accuracy of its causal root cause analyses, verified by human experts, the percentage of AI-initiated self-corrections that successfully restore alignment without needing human intervention, and an overall auditability score reflecting the ease of tracing the auditor's own decisions and ethical rationale.
And its own ethical assurance. How do we ensure the auditor itself is ethical?
It has built-in safeguards, proportionality and transparency. Its monitoring activities must be proportionate to the assessed risks and all its actions transparently logged. Privacy by design. All data processing must adhere to the strictest anonymization and privacy protocols. Contestability. There must be clear mechanisms for human experts to challenge the audit agent's findings and reasoning, ensuring human moral authority remains paramount. And crucially, continuous improvement. The auditor must regularly evaluate its own performance against its constitutional ethical principles, employing its own metacognitive loop for self-assessment and improvement. It's akin to applying computational psychotherapy to the auditor itself to keep it healthy and aligned.
Finally, maintenance and future-proofing. How does it stay relevant?
It needs adaptive learning. The audit agent must continually learn from new ethical dilemmas encountered in the wild, evolving societal values reflected in new regulations or discourse, and the emergent behaviors of the AI agents it monitors. It needs to constantly update its ethical models and diagnostic heuristics. It should prioritize open standard integration, making it easier to connect with evolving open standards for AI ethics, data provenance, and interoperability tools developed by the wider community. And maybe it periodically engages in speculative design integration. This could involve leveraging generative AI tools itself to proactively explore potential unforeseen ethical dilemmas or negative societal impacts of even more advanced future healthcare AI and integrating these insights into its future audit protocols, trying to anticipate the next ethical crisis.
Wow. We've truly gone on a deep dive today. We've explored how artificial intelligence is fundamentally reshaping healthcare, from revolutionary diagnostics and hyper-personalized therapy right down to the basic operations of hospitals themselves. We've unpacked the astonishing potential, but we've also confronted the really complex ethical tightrope we're walking. And importantly, we've discovered some of the innovative architectural and governance strategies being designed hopefully to keep this powerful technology aligned with our deepest human values.
Yeah, we've seen how the very features that make AI so powerful, its autonomy, its learning capacity, its sheer complexity, also make it potentially dangerous if not developed and deployed with extreme care and foresight. This really requires us to think deeply, constantly about critical issues like bias, trust, transparency, accountability, and the delicate, evolving relationship between humans and these increasingly intelligent machines in the context of our health.
So, what does this all mean for you, the listener? As AI becomes an increasingly integral part of our health journey, influencing everything from the scans we get, the diagnoses we receive, the treatments we're offered, maybe even our mental well being support, we're not just witnessing a technological revolution, we are actively participating in a profound redefinition of care itself. So, the provocative thought maybe is this: what responsibilities do we have as individuals and as a society to actively demand not just intelligent AI in our healthcare, but ethical, fair, and deeply humane AI? How do we ensure that this massive architectural transformation truly builds a healthier, more equitable future for absolutely everyone?